so let's move to the case 1 diffusion couple. The material system we choose actually is the diffusion couple, and how to formulate the diffusion equation for the diffusion couple, and also use the initial boundary conditions to get the concentration profile of diffusing atoms. So we're starting from the diffusion equations, and as you see here, the diffusion equation belongs to partial differentiation equation with two variables, x and t, is the location and the time. So in order to get the solution of concentration profile, it would be better to convert this partial differentiation equation to the ordinary differentiation equation with just one variable. So let's try to introduce a dimensionless variable, eta. Eta here we define contain these two variables x and t becomes x divided by square root of 4dt. So the following part will be like this. We try to convert the partial t to become the partial c and partial eta. Okay, and the right hand side here, eta. And right hand side here, we want to try to convert this to also respect with eta. Okay, so the idea here will be like this way. So based on this, we will successfully to convert this partial differentiation equation with two variables to ODE, ordinary differentiation equation with one variable eta. So how to convert this to here? So first of all, we are going to use the chain rule equation. So sorry, probably I need to delete this part. Okay, so what's the chain rule equation? So chain rule equation actually is a partial c, partial t, and this is c and partial t, partial eta, and also times the partial eta, partial t, partial c, sorry, and you got the 1. This is the rule, this is chain rule. So we just move these two terms to the right hand side, and you got this results, right? And the 1 we want this term, right? So we keep this term, and we need to get the partial eta, partial t. What's the partial eta, partial t? You partial this eta with partial t, so t is 10 to what? -1/2, right? So you partial with t by this 1, so you will get this results. So now we successfully to converted partial c, partial t, converted to partial c, partial eta. And this term, then right hand side, how we deal with is you just let me draw this. You just substitute this. You use the square root 4dt times the eta to substitute x, because x equals to square root of 4dt eta, right? And you square this term and move this term to the front. So what you are going to have will be like this term. So square this one, 40t and eta square, right? So now you got your left term, you have this one, and right hand side you got d times this term. So after arrangement, you got this ordinary differentiation equation with one variable eta. So next, I'm going to try to solve this ODE to get the c as a function of eta. So how to do this? So I copy this equation and allow the q equals to dc over d eta. So you got the minus 2 iota q, and this one actually you just dq over d iota, right? dq over d iota. And next, this is the differentiation equation you're familiar with. So you just move this d iota here, dq here, and take the integral on both sides. So you will get the q1 equals to a1 exponential minus iota squared. And as you know, q equals dc over d iota. So now the story will be moved to here. In order to get the c as a function of iota, so we move the iota to the left-handed side and take the integral on both sides. Okay, so and in order the case we're dealing with is a diffusion couple, and we just use this as an example. So we take the integral on both sides and starting from negative infinity to iota. Okay, so let's take a look here. So because this for dc you take the negative infinity to iota, so you got the c iota minus c negative infinity, and the left-handed side you got the a1 exponential minus iota squared iota. So you take also minus infinity to iota. Okay, you got this result. But this term is familiar with you, right? What are they? What is this? It's similar. This actually is what we call the error function. Error function of z expressed like this. And this term actually is similar with this term, right? And the error function 0 equals to 0. Error function of infinity equals to 1. And error function is an odd function, so error function minus z equals to minus error function z. So it tells you that error function minus infinity equals to minus 1. So based on this, we try to separate this term because the upper or bottom limit and upper limit is negative infinity to iota. But for the error function, usually we'll have a 0 point as a 0 point, 0 as a point, right? So we separate this term to become what? Negative infinity to 0 and plus 0 to iota. Okay, so based on this, we can just, what's the c of negative infinity? It will be like this, right? So it will be cl. So you move to right hand side, you got the cl plus. And this term actually, we try to link this with error function, and also there's a parameter here. So we use a2. We times the 2 over square root pi and use a2 to balance this one. So now an a2 actually is a square root of pi divided by 2. So you will delete it, right? So a2 times this one plus this one. The reason for this is we try to convert these two terms to become the error function. So this is why it's a trick for this one. Okay, so let's take a look for this one. What's this value? This one actually is a negative infinity to 0. And so you can try to switch the upper and bottom limit, so it becomes to 0 to negative infinity. If you do this way, you need to times the negative 1, right? And 0 to negative infinity, so because it is odd function, so it's negative 1, right? So negative 1 times negative 1 will becomes 1. And this one is error function, so no, for sure it's error function. So we got the C concentration as of iota expressed like this. And now you got to use the recess successfully to get the solution, right? C of iota. But now we need to input the boundary conditions. So what's the boundary conditions for this step function or diffusion couple? Will be the iota. Iota is x divided by square root of 4dt. When iota similar to x approach to infinity, then the concentration will be equals to CR. So based on this, you can write down when iota approach to infinity, so this will become CR, right? Okay. And Cr equals to Cl plus A2, 1 plus 1. Because iota approach to infinity. So now you get the A2 will be Cr minus Cl divided by 2. So you got the A2. So now you know the A2, you just substitute this term back here. So you can rewrite the concentration as a function of x and t. You need to decouple the iota to become the x divided by square root of 4dt. Under this situation, you got the solutions for this diffusion couple or diffusion equation would be what? The average of sum Cr plus Cl and the average of difference between Cr and Cl error function iota. So this is a solution for diffusion couple. And some interesting stuff you need to keep in mind. There are 3 important points that does not change with time. The first one is the x equals to 0. The concentration at here, for sure, when you have a 0 here, will be the average of Cr and Cl. And for positive infinity and negative infinity, the concentration will become Cr and Cl. These 3-point locations, the concentration does not change with time. As long as it changes with time, that implies that the boundary condition changes. That means you cannot use these solutions for this your diffusion couple. And in most cases is when the length of this diffusion couple is too small, and under that situations, the infinity, the positive infinity, because this is so small, the length is short, like this way, and the boundary condition, the concentration at inside this materials is not Cr, and this is also not Cl. Under this situation, you cannot use these solutions for this kind of diffusion couple. Don't forget that. So let's draw something. If the length is like this, just this diffusion couple like this, and you can observe the concentration here. Probably I use this as an example. When the Cr diffuse through the left-handed side, the concentration profile after T1, right? Then you can see the concentration profile. But because the length of this diffusion couple is so short, so the concentration at the left-handed side at this edge cannot be equal to 0, right? Or cannot be equals to C at all. So under this situation, there's usually will diffuse back. So the profile will become like this. And under this situation, the location at this left-handed side, the concentration at this left-handed side will change with time. So under this situation, you cannot use these solutions for this diffusion couple. So for diffusion couple, usually diffusion length is smaller, much smaller than the total length of diffusion couple. That can allow, under any situation, diffusion time period, the boundary condition, this, and this, always satisfy. This boundary condition should be satisfied. So in that case, you can use these solutions. Okay, so this slide actually just for your reference, you know, we always provided this table to allow you to check the value for error function z. And also this is the complementary error function. You use the equals to 1 minus error functions. So now I'm going to give you an example here. It's a nickel copper diffusion couple. And what we have here is we have the pure nickel and copper nickel alloy. And we also assume diffusion length is much smaller than the total length of this diffusion couple. And based on the information we have, we are interested in the concentration profile of copper. So copper, we have copper here, no copper on our left-handed side. So when you try to plot the concentration profile, it can be like this step function. And based on the data provided in these questions, we got the diffusivity is as a function of temperature, activation energy, and also the D0. And we also need the D0 activation energy. And the temperature here we assume is at 400 degrees C, so you need to convert it to absolute temperature, and you will get the diffusivity of copper expressed like this. So based on this, I'm going to directly use the results we derived from previous slide. Would be the concentration of copper can be the average sum of this one plus this one, and the average of difference between the difference between this one, and take the divided by 2, right? And arrow function eta. So you can write become this. And based on these equations, we know the diffusivity, right? So as long as you know the time, then we can plot the concentration profile. So based on this, if T equals to 0 before diffusion, the concentration profile is like this orange line, origin curve. And after 5 days, the profile 5 days, and also input diffusivity show here. So we will get this black curve. And after 25 days, then we can get this light orange curve. Okay, so this is the example for how to formulate or how to get the concentration profile for the diffusion couple. Okay, so today we ended here.